It's my pleasure now to introduce the person who will introduce our speaker this evening, Dr. Steve Davis, Distinguished Professor of Biology. And we're very thankful to Steve because he's the one, I think, who helped us get Dr. Chris Field tonight. So please join me in welcoming Dr. Davis.
Our speaker this evening received his PhD from Stanford University in plant physiological ecology in the early 1980s. His research was on a native plant to California, much like the one seen here that grows in the natural landscape of the Malibu campus. On individual leaves, Dr. Field measured two of the most vital processes that sustain all life on Earth. The uptake of carbon dioxide from the atmosphere, we call it photosynthesis, and the loss of water vapor, we call it often transpiration. But significantly, he scaled up from the individual leaf to see how it coordinated the whole plant process, and more importantly, how that facilitated the plant function in its natural ecological setting. At the time, there were no portable instruments commercially available to do this kind of work. So what Dr. Field did was he opened a book, pulled out a soldering iron, and he built a field portable gas exchange system. So here's a photograph on the top left of Dr. Field in the red baseball cap with his system in the hottest, driest, most inhospitable location on Earth, Death Valley. Great training for a future climate change biologist. Down on the bottom right, you can see this chamber where he's placed his leaf from a desert plant, and he's measuring photosynthesis and transpiration. And today, again, he is scaling up, but this time to monitor the metabolism of the whole Earth and measure its health. He has not yet found a chamber big enough to fit over the entire globe, but he relies on indirect methods. Dr. Christopher Field is a founding director of the Department of Global Ecology at the Carnegie Institute of Science. He's a lead author and co-director for the International Panel on Climate Change. He's a director of the Jasper Ridge Biological Preserve, a member of the United States National Academy of Sciences, and professor at Stanford University. His talk this evening is entitled The Velocity of Climate Change. Please join me in giving him a warm welcome to Pepperdine University.
Thanks, Steve, and thanks all of you for joining me tonight. And I wish I could join you for my good friend Condi Rice's lecture in a few weeks. You should ask her about climate change as well. What I want to do, is the microphone working? I'm hearing lots and lots of static, but can't tell if it's actually amplifying. Okay. My coat is hitting my tie. Okay, what if let me try buttoning the coat. I apologize for this technical glitch. Do you have some advice for me? Okay, I apologize for the delay. So what I want to do tonight is talk with you about where I think we are in the scientific community on understanding climate change and how that should inform an important and legitimate societal debate about what to do about it. I've entitled the talk The Velocity of Climate Change, and some of the remarks I want to make are about how fast climate's changing, but I view velocity in a much broader context, and that's the one I really want to focus on. The velocity of the changes in the impacts, the components of climate change that make it spread out over many decades or centuries, the reasons that human responses might be slow and the reasons that they might or might not be delayed. what is important to recognize from the very start is that climate change is an issue of such diversity, such complexity, and such a wide range of stakeholders. It's essentially unlike anything we've ever dealt with in a world community before. And what I would like to do and share with you is a philosophy about bringing all the parties to the table to have a good discussion about the options. As a scientist, my job primarily is to present the scientific information on climate change in a way that's as balanced and unvarnished as possible. And that's what I want to do tonight. But beyond that, I also want to present what I think are some of the key interfaces with the dialogue about policy options. My goal as a science communicator is to make these issues as clear and as simple as possible. And my model in doing this is Tom Tolles, who always seems to get to the core of an issue in just a few words. So the basic theme of this cartoon is the idea is it's 2060 and the search for a breakthrough technology continues, and the technology is that it's a time machine. And the hope is that it takes them back 50 years to when they should have done something about climate. And you know, I think that's the essence of the climate change issue. We want to avoid being in a situation where we have deep regrets about not having done something when we should have. And I want to make sure that we have the information that we need to make the good decisions, but also ask what are the other components that are required to enable good decisions. And let me start with what's kind of the organizing theme for at least the international dialogue on climate change, and it's the UN Framework Convention on Climate Change. This is Article 2 that says what the goal of the convention is, and it has two important components. The first important component is that the goal should be to prevent dangerous anthropogenic interference with the climate system. This is a really challenging statement. It makes it seem like there's some bright line at which it's not dangerous before and it is dangerous over. I think from the scientific perspective, this is not the most useful framing, because we probably have already encountered a situation where climate change is dangerous already for some people in some places, and where for other people in other places there might be benefits to climate change. The second important operational component of Article 2 is one about velocity. Within a time frame sufficient to allow ecosystems to adapt naturally to climate change, to ensure that food production is not threatened, and to enable economic development to proceed in a sustainable manner. So the convention specifically looks at ecosystems and the rate at which they can adjust. It looks at food production and the rate at which it can adjust. And importantly, it looks at sustainable development and acknowledges intrinsically that this sustainability component has two dimensions. You don't want the climate change to proceed so fast that it prevents economic development, but you also don't want to invest so much in economic development that you pull critical resources away from climate change. This velocity issue is, I think, the most challenging component of the International Framework Convention that is essentially you could think of it as the outline for the way that the world has decided to approach climate change. Throughout the material that I want to present this evening, there's no concept that's more important than the concept of risk. And I think everybody has a gut understanding of what risk means. In formal technical language, we talk about risk as the product of the probability of some event times its consequence. A high probability, low consequence event can have the same risk as a lower probability, higher consequence event. And to help people understand the way that risk influences thinking about climate change, it's useful to consider a couple of analogies. And the top two have been widely used. My late colleague Steve Schneider talked about climate change as playing a game with loaded dice. Say 2 ones is the outcome we don't want to see, and as the climate changes, we're loading the dice so that they become progressively more likely to come up with the ones. We don't know when the ones are going to come up, but we know that we're loading the dice. John Holdren, the president's science advisor, uses the analogy that with climate change you can think that it's like driving a car toward a cliff in a fog. We know there's a cliff out there somewhere. We don't know where it is, and what are the things that we should do in order to not drive off. I want to talk about a different analogy, and it's one that's been helpful for me to think about the full range of options and the full range of impacts. I think of the global economy as something that produces wonderful benefits, but a side effect of the way we've set it up is that it kind of dumps nails on the highway of life, and we're following along in a series of vehicles. Some are brand new and have great tires, some are old and have bald tires, and the more nails there are on the road, the more confident we are that people are going to have flat tires. Initially, they're going to be inconvenient. There are going to be some people for whom the flat tire leads to loss of control and a catastrophic accident. As these accidents become more and more frequent, there's an increasing probability that there's going to be multi-car pileups and potentially catastrophic pileups that involve car after car after car. I think that this dumping the nails on the roads of life analogy sort of captures a sense in which we're likely to see the consequences of climate change. It's going to be the most vulnerable stakeholders who experience the impacts first. Some of those impacts are going to be minor. If you were the operator of a tire repair station, you might view climate change as a big benefit, and there will be some beneficiaries. But it also illustrates the potential of climate change to interconnect, so that stakeholders who are very well adapted may not be able to avoid the impacts of climate change if that is realized through their car being right behind a car that has an accident. Another feature of the dumping nails on the roads of life analogy that I like is it characterizes the solution set in a useful way. One thing we could do if our economy was producing a nail-strewn highway is we could adapt. We could get much better tires for our cars so that the nails don't puncture them. And that's what rich countries can do. If you're poor, you have much less access to the adaptation strategies. Or we could change the economy so that it dumps fewer nails. And that would be setting up new technologies so that we can produce energy in a way that doesn't release greenhouse gases to the atmosphere. A third thing that we could do is we could put like a sheet of paper over the nails so that the first couple of cars who drove over wouldn't be exposed to them, but it wouldn't last very long. And that's a set of strategies that are often called geoengineering or solar radiation management, where we try to change the atmosphere to reflect solar radiation away. That last one is a very poorly understood set of options, but it's one that we should understand more about. The core question that I want to talk with you about tonight is not is climate change going to produce a catastrophe, or are we certain about it, but how much information do we need to have in order to make smart decisions? You know, climate change is fundamentally a problem of risk and risk management. We make decisions under uncertainty all the time. Every time we decide whether or not to wear a bike helmet when we go out on the bicycle, buckle the seatbelt, buy car insurance. Every time we decide to make financial investments, we're making those decisions under uncertainty. And I would argue that as a society, as a global community, we have lots of tools for making decisions under uncertainty. And I think that the key bottom line of what I want to share with you tonight is how we can apply those tools in order to make good decisions about investments in dealing with climate change. To get to that material, I want to frame it in the context of velocity. And velocity has a bunch of different components, as I already said. One is how fast is the climate changing. I want to talk for a couple of minutes about the history of understanding climate change. This is a science body of information that's really unfolded and evolved over more than a century. I'll talk a little bit about what the implications of the rate are for how fast ecosystems need to readjust. Talk about the concept of velocity in the context of commitments. How fast are we entering situations where future activities won't get us away from undesired outcomes? And then I want to conclude with some thoughts on the pace of the human responses. This is the trajectory of global land and ocean temperatures over the period that we've had good thermometers since the later decades of the 19th century. And at the top I have the statement about the status of the climate system from the last report of the Intergovernmental Panel on Climate Change, where the conclusion was that warming of the climate system is unequivocal. Based on this and many other temperature records, it's clear that the climate system has warmed by an amount that's still less than 1 centigrade degree, but rapidly approaching it. Over the last several decades. But it's a complicated picture, and many people have pointed out, and appropriately pointed out, that there was a period of rapid warming from the 20s through the 40s, not much change from the 40s through the 60s, and then a period of rapid increase since then. There has been a lot of speculation in literature that something different has been going on for the last several years, and it's certainly true that 2008 was a cool year in terms of the global numbers. But at least for me, I don't see anything that looks qualitatively different about the last decade than about the last 50 years. 2010, based on this NASA record, is basically tied with 2005 for the warmest year in the record. Essentially, the message from this is that there is absolutely no doubt that the world is warmer by almost a centigrade degree now than it was in the late 19th century. And this is one part of a body of science that really doesn't leave much doubt about the fact that the climate is changing. But there is a lot of doubt about other aspects of climate change, and I want to talk about some of those. The first aspect about future climate change that's uncertain is the question of what are people going to do in the future? These are pictures of kind of possible visions of what future society might look like. You know, we might, in terms of the emissions of greenhouse gases, we might live in a society that emphasizes energy from fossil fuels, is energy intensive. We might emphasize a society that uses high technology approaches to generating energy. Or we might use one that's not heavily industrialized and emphasizes diversified local approaches with emphasis on things like information technology and services. And those have a lot of leverage over where the world goes. When we look at the current uncertainty in climate change projections, something like 60 to 70% is in this area of what kind of decisions people and societies make independent of climate policy. And the other 30 to 40% is in the technical aspects of the physics and the biology of the climate system. Here are the projections of possible global average temperatures for a number of these internally consistent framings from 2000 to 2100. And the 2 points that I want to make here are that more emissions lead to greater warming. There's very little doubt about that. But the key thing I want people to recognize is that there's a significant amount of uncertainty around each of these outcomes. So these gray bars to the right of the figure are the 66% probability range for the final outcomes of each of these scenarios, going from the diversified solutions through the fossil intensive, showing the most likely estimate, but the whole range. And as risk managers, we want to think hard about the implications not only of coming out in the middle of the range, but at the upper end especially as well. And the IPCC talks about a sort of a canonical range of uncertainty with the 2100 temperatures between a warming of about 1.5 C and about 4.5 C. But one thing to note is that the uncertainty range for the highest scenarios goes above that, and that with the highest emission, the best estimate is up around 4 C. There's a huge difference in the projected impacts between a world that in 2100 is 1.5 C, a little less than 3 Fahrenheit warmer than it is now, and 4.5 C, which is about 7 warmer than it is now. And the implications of this are that we would be very unwise to think about climate change as a fixed number that we're trying to manage. This uncertainty means we're shifted into this risk management profile, and we need to decide how to make smart decisions, not the right decision, because there isn't any decision that's fundamentally right or wrong. Let me talk for just a couple of minutes about how our understanding of this problem has unfolded. The scientific communication of climate change information into the policy domain has been going on for many decades. Here are a couple of statements from 1965, probably one of the most important ones. The first time that the U.S. scientific community really went on the record as indicating that climate change is a potentially serious problem was in this National Academy of Science Charney report from 1979, where they said, if carbon dioxide continues to increase, we find no reason to doubt that climate change will result and no reason to believe that these changes will be negligible. A lot of people thought that when this report came out, well, we'll come up with some way to deal with climate change, and that by the time we reach the start of the new millennium, it'll be a solved issue. That obviously hasn't happened, and we want to think a little bit more about why that is. But if we want to trace the scientific roots of the understanding of climate change, we really need to go back farther. This is the cover sheet of an 1896, more than 110 years ago, paper by the brilliant Swedish chemist Svante Arrhenius. And in this study, Arrhenius did a number of amazing things. He was a student of the absorption of heat by atmospheric gases, and he understood that carbon dioxide, what he calls carbonic acid in this paper, absorbed heat radiation that as a consequence could warm the world. And he used very creative measurements of the light that was reflected from the moon to figure out how much heat energy was reflected. And then he did a series of calculations that said, well, how much might a doubling of CO2 warm the planet's surface? And the extent to which the problem was basically understood then in 1896 is really staggering. Arrhenius knew that sooner or later much of the CO2 that was released in the atmosphere would dissolve in the oceans. Arrhenius knew that a warmer atmosphere would tend to create an increase in water vapor evaporation, and because water vapor is a strong greenhouse gas, you'd get an amplification from water vapor. So what's really critically important to note is that by 1896, the core components of the physics of the way that greenhouse gases alter climate were really established, and they basically haven't been contested since then. There are lots of important feedbacks that can either amplify or suppress the overall magnitude of the response. But these core concepts of the way the gases interact with radiation are understood at the same level of completeness as, for example, the way a transistor works or an electric motor. But the important uncertainty concerns the overall sensitivity of the climate system, the sensitivity that has lots of these feedbacks built into it. The range that the IPCC gives for the climate sensitivity, which is defined as the amount of warming we would get with a doubling of the carbon dioxide concentration in the atmosphere, is from about 2 to 4.5 degrees C. And importantly, the IPCC in its 2007 report concluded that higher values of climate sensitivity cannot be excluded, that we might end up with more warming than the warming consistent with a 4.5 degree sensitivity. If you're a risk manager, that's a scary statement that says we're not really sure that those ranges that we're presenting actually include the most serious consequences, where, remember, if we're defining risk as probability times consequence, we've got a really high consequence and an unknown probability. A student who worked with Steve Schneider and me, who just finished her thesis last year, just completed a very nice study that took advantage of a wide range of temperature proxies from ocean cores to revisit this question of the sensitivity of the climate system to changing CO2 concentrations. And she concluded that the IPCC range is fundamentally pretty close, but is probably biased slightly toward the low side, so that her best estimate is a climate sensitivity, this is the amount of warming for a doubling of CO2 of about 4C, as opposed to the IPCC estimates of 3C, with the conclusion that it's relatively unlikely that the number is higher than 6. But 6 centigrade is a huge amount of warming. That's a greater amount of warming than we've considered with any of the climate model simulations, and it's one that we would really want to think hard about committing the world to. Okay, I want to talk just for a couple of minutes about impacts, and I'm going to focus on California. Just to kind of set a frame, I don't want to say these are the specific impacts we might expect. And with most of these impacts, I've chosen to present 4 pictures from 2 climate models that captures the diversity I was explaining, and that some models are more sensitive and some models are less sensitive, and also the contrast between emissions scenario in which there's either higher or lower emissions, you have a world that's focused on fossil energy or not. And in this picture, the low emissions scenario is here, and the higher emissions scenario is here. These color bars are in centigrade degrees, so 10 centigrade is 18 Fahrenheit, 18 Fahrenheit for wintertime and summertime. And what you can see is that for California, the end of century projections are for warming in the wintertime that's significant, more than 3 or 4 C, but much greater warming in the summertime. And with this business as usual emissions, the summertime warming over much of California could be as much as 7 C or greater. These are huge temperature elevations way outside the range of historical observations, and they're things that would fundamentally reshape what the experience of living in California was like. I mean, just to characterize the difference, it's the annual mean temperature difference between Los Angeles and Death Valley is about 6 C. It's interesting, for California, the climate models really want to put this bullseye of warming over Sacramento, and I don't know if there's a message in that, but it always comes out that way. So let me just talk about 3 impacts. And it's hard. We know a lot about the impacts of climate change, but we don't know which ones are going to be most important. Most of the information we have to date is that in California, issues with water availability, wildfire, and sea level are likely to be important. But a lot of the climate impacts I worry are things I call social teleconnections. And those are connections that are transmitted over long distances by things that people do, or things that markets do, or things that ecosystems do. And an example is if climate change created impoverishment in some part of Central America that led to armed conflict, might we see migration pressure across the southern border of the United States. These teleconnections are very poorly understood in terms of the scientific characterization, but I think they have the potential to be quite important. Let me talk first about water. California, as probably you know, has a really impressive and important water storage system. That water storage system consists of 2 major components. One is a big series of reservoirs, and the other is the snowpack in the Sierras. If you look across the U.S. and ask where is the snowpack component of this storage vulnerable to a small amount of warming, what you see is that the vulnerability is greatest along the Pacific Cordillera, especially in the Sierras. And these are places where wintertime snowpack temperatures are relatively close to freezing. So a small amount of warming converts you from below freezing to above freezing. That's an important threshold, not so much in the climate system, but in the water storage system. And so one of the things we can ask are, well, what are the implications of future warming for California of this vulnerability? And this isn't the world's clearest picture, but it's basically a map of California for a low emissions and a high emissions scenario. And the color bar here is how much of the current snowpack still remains at the end of the 21st century. For the lower emission scenario, this is 27% of the snowpack remains. For the higher emission scenario, it's 11% of the snowpack remains. Basically, the climate models are telling us that the ability of the Sierras to create a major water storage reservoir essentially goes away under either low or higher emissions. California has more than a century of conflicts over water. And this isn't a new component of the climate water conflicts, but what it is a new complication. And I think that throughout the world, what we're likely to see is climate change isn't necessarily going to cause new problems. It's going to cause new twists and new complications on old problems. Here's the risk of wildfire across the western states based on historical data. And this is plotted as the sensitivity of the area burned on an annual basis to a 1 degree of warming. And what you see is that there's a dramatic sensitivity of much of the western U.S. These numbers are 300% increase in area burned, 200% in the Central Valley, 470% in northern Arizona, and not a big effect in coastal Southern California. Obviously, this is a very fire-prone area, and it'd be interesting to know what will happen here and whether the risks of fires really get to be a lot greater. And the science so far in this has a really interesting twist. And it's illustrated here in this paper by Tony Westerling. And the basic idea is if you look at climate models that tend to be wetter in the future, you see an increase in area loss to wildfire. This is basically the number of large wildfires you can think about it is for a lower emissions and a higher emission scenario for Southern California in the blue and Northern California in the red. But if you look at climate models that produce drier scenarios, you tend to see a decrease in the number of big fires in Southern California, even though you see an increase in the number of big fires in Northern California. And the analysis that Tony did on this suggests that essentially what's happening in Southern California is the frequency of wildfires is being controlled by whether there's enough precipitation to grow enough vegetation to carry a wildfire. And if you have a wetter future, that you get enough vegetation so that the warmer temperatures can cause more fires. If you have a drier future, you basically have temperature conditions that are fire friendly, but not as many fires because it's so dry and no plants grow. The final impact I want to talk about in a Southern California context is sea level rise. Sea level rise has been a really difficult problem for the scientific community to deal with because it has two important components. One's the fact that warmer water is a little bigger as a consequence of thermal expansion. And the other is that if ice on land melts and runs into the water, there's more water in the oceans. And the IPCC projections shown here in this picture, this from a paper by Dan Kyan and colleagues, has the IPCC range of sea level rise for the end of the century, basically 20 to 60 centimeters, 1 to 2 feet. And the picture in the lower right has the projections from Stefan Rahmstorf from the Potsdam Institute for Climate Change Impact Studies, where he has included the most likely consequences of a change in land ice contributions to melting water. And we know that over the last decade or so, 80% of the sea level rise we've seen globally has been a consequence of melting land ice and not of the thermal expansion. So I think that the evidence is pointing toward this range as being a more likely one for the 2100 time frame. And you can see that here we're looking at an uncertainty range from about half a meter to about 1.2 meters of global average sea level rise. Coastal California will probably see about that much. The range, of course, is very important. Huge difference in impacts between half a meter and 1.2 meter. And both of those sound like pretty small numbers. And, 1.2 meters, about that much. And you can imagine a wave line that was that much higher up the beach. But what's really striking about sea level rise is what you care about is what happens when you have a storm during the highest tide or when there's a spring flood at the same time. And you can think of that as the exceedance. What's the probability that we're going to have a high water event that's outside the 99.9 percentile? And Kayan studies provide a very nice example of how this exceedance likelihood goes up as the sea level goes up. So with zero sea level rise over 100 years, you might get 10 to 30 extreme events, where the extreme event is being defined as being outside 99.99% of the records in the historical record. But at half a meter, you're looking at 100 to a few thousand by the end of the century. And if this one only went up to 80 centimeters, 0.8 meters, and the Rahmstorf estimate would say that we could go up to 1.2 meters. We're looking at a progression that takes us up to potentially as many as 20,000 or about 1,000 times as many exceedances. In climate change, the damages really pile up on the extremes, and this huge increase in exceedances is exactly the kind of thing that we would be worrying about in terms of the impacts. Okay, so that's a snapshot of sort of why to think about climate change in California. I want to step back and say just a few things about other components of velocity and then come and tie this line of thinking together. One of the things we'd like to know about the velocity of climate change is how fast would ecosystems, communities, activities have to shift? And we can get an estimate of that because we know current spatial patterns of climate variability, and we know, at least from climate model projections, how fast the climate might change in the future. And we can combine these two into a velocity of climate change, saying how fast would a plant or an animal have to move in order to stay at a climate that's like the climate it's in now. And we know from historical records, pollen that could be extracted from bogs and stuff like that, that following ice ages, ecosystems can move at something like a tenth of a kilometer per year, 100 meters per year. And when we did this study with kind of an average amount of climate forcing, we found a pattern that was relatively surprising. The first surprising thing about it is that the average rates of movement depended strikingly on the landscape topography. It was the big flat areas that had the highest required rates of movement because the current spatial gradients of temperature are so shallow there. The other thing that was surprising is how fast the rates were. I already mentioned that the historical fastest rates we've seen in the fossil record are around a tenth of a kilometer per year in the blue colors here. The global average for this study was about 0.4 kilometers per year, or more or less 1 yard per day. And the Earth has 31% of its area with climate change velocities that are greater than 1 kilometer per year, or 10 times the fastest rates that we've extracted from the fossil record. So basically, we're looking at a future with a modest amount of climate change where we're really asking ecosystems to scramble. And you may say, well, you know, if you're a butterfly or a lizard or a mountain lion, a yard per day doesn't seem like it's all that much. But ecosystems are complicated beasts. And if we look at the kinds of changes that have occurred so far, we see some important trends. We know that some things can shift. In this paper by Parmesan and Yo, they found that when they looked at a large number of range boundary changes and changes in the timing of activities, that there was an average shift of 0.6 kilometers per year, just about the same as we project to be required. But what they also found was that there were some things that were good at moving and some things that were bad. If we look across the kinds of ecosystems and species we care about, I think there's a frustrating misalignment between the things that are good at moving and the things we care about. So this is a butterfly that's currently extinct on Stanford's biological reserve. It's extinct because the habitat's very fractionated, and it's a butterfly we know is okay at moving, but it's got to have some place to move to. This is yellow star thistle. It's a horrible invasive in California, but it's very, very good at moving. And what I see is climate change opening a series of targeted opportunities where the fleetest and the best movers take advantage of them. And so far it looks in California like star thistle is going to be the winner, and it's hard for me to imagine that we're not looking at a future that's weedier and weedier. To an extent that's surprising lots of scientists, we're seeing a whole stand die-off of lots of important species. That's a dead stand of aspen trees in Colorado, and in the last several years we've seen a large-scale mortality in tree populations in Colorado, Arizona, British Columbia. So I think what we're seeing isn't little adjustments. We're seeing lots of places where stands die out. But then finally, it's important to recognize that some ecosystem processes unfold on a scale that's so long relative to the human processes that we might not even know if the ecosystem shifted out of its zone of climate preference for centuries or more. And you know, when you look at the giant sequoias, it may be that they haven't been in a zone that's climatically favorable to them for a millennium or more, but they may just be able to persist for another millennium. So I think this kind of diversity between the things that are good at moving but habitat limited, the things that are good at moving and opportunistic but we wish didn't move, large-scale die-offs, and kinds of organisms that have tremendous staying power, whether or not the climate's appropriate, paints a very complicated picture of what future ecosystems are going to look like, and we're only beginning to unravel the threads on which each of these processes unfolds. Okay, now I'm going to switch gears, and I'm going to talk about a couple of climate processes that I want you to have in the back of your mind when I return to the topic of what we should do. The first is a question about how long climate change lasts. I told you earlier that Arrhenius knew that if you put CO2 in the atmosphere, eventually most of it, about 80%, goes in the oceans. That 80% decay occurs over a period of a few hundred years. That decay rate is shown in the top figure here, where these experimenters in my laboratory injected, at least in a computer model experiment, a big pulse of CO2 in the atmosphere and then let it decay away. What they expected, and what everybody kind of expected, is as this CO2 concentration decayed away through uptake by the ocean, that the warming would decay away as well. But the warming is what's shown in the bottom plot, and you can see that even though the CO2 is down to about half of what it was at the start of this 500-year simulation, that the warming basically stayed about the same. And there have now been a bunch of studies that have confirmed this, that warming that's caused by injecting CO2 in the atmosphere is, based on any time scale that we'd like to care about, essentially permanent. It lasts for centuries or millennia. And the physics behind this are relatively well understood. Basically what happens is, as the CO2 concentration goes down as a consequence of uptake by the oceans, the ability of the oceans to take up more and more heat goes down at about the same rate. Essentially, the bottom line you need to think about is that if we commit to climate change, we commit to it for a millennium. A lot of responsibility. Okay, the next thing I want to talk about is the question of how much climate change are we committed to as a consequence of the stuff we build, the power plants, the energy infrastructure. This is a wonderful Ansel Adams photo of Hoover Dam, and Hoover Dam is not a CO2 emitting structure, but it's the best photograph of the most artistic photograph of an energy infrastructure structure I could get, and it really emphasizes the solidity and long-term investment that this kind of infrastructure represents. If I were to build a coal-powered power plant, that would typically represent something like a 50-year investment, and early retirement would represent a great expense, something I wouldn't want to do. So when I think about energy infrastructure, what I really want to think about is that the power plant that gets built tomorrow is a power plant that's still going to be in operation in 2050. So I'm really committed to the climate change consequences of that power plant and of the society that it represents. So in a very nice study that was published in Science last year, Steve Davis and colleagues said, okay, well, how much climate change are we committed to, not by this sort of the permanent stuff that I talked about, but just by the fact that we've got long-term durable infrastructure that's going to be emitting CO2 for some time in the future because it's new. And the results are shown here, that if you just say how much CO2 comes from all the stuff we've got now, you get CO2 coming out of it for the next until about 2050, and that represents contributions from each of these processes, with most of it coming from the fact that power plants last for a really long time. Transportation, this orange one here, you can see decays substantially more quickly because cars don't last nearly as long as power plants. If you ask where in the world these committed emissions come from, you can see that the place where they really tend to play out over a long period is China in the light purple here, because China has a lot of stuff, and that stuff is all new. In the U.S., in the blue here, you can see our committed emissions fade away relatively quickly because we have a mix of different ages, including some that are scheduled for retirement now. From the perspective of a citizen in the U.S., this is a huge opportunity. We're committed to building new stuff. We have an opportunity to build the stuff we want to have for the next 50 years, rather than the stuff that we might have made a mistake building 5 years ago. And if you look at how much CO2 concentration we're committed to as a consequence of this stuff that's already built, it pushes us up some, but it's not a terrifying number. The current concentration of CO2 in the atmosphere is around 390 parts per million, and there's some uncertainty about how much committed emissions are from the infrastructure that exists. But it looks like the most likely consequence of the emissions that we're committed to is a CO2 elevation of only about 20 parts per million. That's a lot, but it also means that we have a huge opportunity to alter the trajectory by decisions that are yet to be made. And I think that this is an incredibly exciting outcome, because it says that in terms of investments, in terms of understanding, and in terms of decisions about the future, we don't have a hugely unacceptable level of climate change baked into the system. I love this picture. This is says something about the permanence of the infrastructure we build to adapt to climate change. This is called the Thames River Barrier, and it's a huge infrastructure built across the Thames River where these gigantic gates come up every time the Thames is likely to flood. Represents a kind of 100-year investment for the City of London, been incredibly important in protecting their infrastructure. It was designed in the 1950s with the expectation that it might be used a few times per decade, and now it's used many times per year. But it also indicates that when we think about long-term investments and durable investments, we need to think not only in the area of the energy generation technologies, but also of the adaptation technologies. So, I mean, this brings me to where I want to close, and I want to talk for a few minutes about what you do. And there are three things we could do. We can mitigate. We can decrease the amount of climate change that occurs by decreasing the emissions of greenhouse gases. This is the decreasing the rate at which we dump the nails on the highway of life. We can adapt. We can come up with coping strategies like the Thames River Barrier, or buying new tires for the vehicle that's on the road covered with nails, or we could delay. And I want to talk about the implications of each of those. There's some advantages to delaying. You can argue that, well, we are not really that certain with the science, and we know that investments in avoiding climate change are going to cost something. If we delay, we could avoid unnecessary expenses and allow progress with the technology. We also could start from a position where the global wealth was greater, and where potentially sort of the rising economy lifting all boats philosophy might mean there were fewer people and ecosystems in vulnerable settings. But the consequences of delay are really quite scary. There was a paper published a couple years ago that looked at output from all the world's leading integrated assessment models. These are the models that do the economics of climate change. And they said, okay, let's look at what we would need to do in order to stabilize CO2 concentration at 450, 550, and 650 parts per million with or without delay. And what they found is if you want to stabilize at 450, kind of the nominal 2-degree warming level, you couldn't do it if you allowed a delay. That we simply can't think, in the context of the way these models work, of a series of societal actions that would let us stabilize CO2 at 450 if we delay for more than about a decade. If that's the target, we simply need to act now in order to reach it. Even if we want to solve at 550 parts per million, which is a nominal warming of around 3 to 3.5 C, 5 of the models say that there's no way that they can think of an economy that could reach that level if there's a delay of more than about 20 years. So the big challenge with delay is that because we're building stuff now that's going to control the trajectory, we don't have very much time. And the consequence is that if you want to solve the problem, you don't have a very big window. So should we mitigate? And the argument against mitigation is that, well, I told you how much uncertainty there is. We might decrease the uncertainty, and we also have a lot of uncertainty about what it would cost to mitigate. But the contrast between what we know about the costs of the climate damages and the costs of the mitigation is really striking. The best estimate we have of the costs of the climate damages probably comes from the Stern Review. It's kind of the official advice to the British government. And they concluded the Stern Review concluded in 2006 that the cost could be anywhere from 5% to 20% of global domestic product every year, continuing into the indefinite future. From what we can tell about the cost, the IPCC estimate is that in 2050, the cumulative cost of aggressive efforts to stabilize climate at a CO2 concentration somewhere between 475 and 550 parts per million might be between a net benefit to the economy of about 1% and a net cost of about 5.5%. What's that mean? So that means that consider whatever level of wealth the world would be at in 2050, if we make aggressive investments in mitigating climate change, we would delay the global scale of achieving that wealth by 1 year. Essentially, we would be asking the global community to defer by 1 year, reaching the wealth of 2050, in order to be confident of avoiding the worst impacts of climate change, even though we still don't know exactly what those impacts are. So what about adapting? Again, we have the same two major features. We have lots of uncertainty about what the impacts are of doing nothing. We have uncertainty about what it costs to do the adaptation. But one of the things that's most interesting about the adaptation agenda is that essentially everything you can think of doing to adapt to future climate changes would improve resilience to current climate variability. We're talking about things like protective barriers like the Thames River barrier. We're talking about things like better insurance systems so that affected stakeholders can be compensated. Thoughtful strategies about moving populations away from places where sustainable economies are no longer tenable. So all of those are things that make sense in the context of current climate variability, and in many cases would be a good idea to do even in the absence of climate change. There have been lots of studies on adaptation that have concluded that adaptation is one of the kinds of social mechanisms that typically pays for itself several times over. And so I think there are real benefits in adaptation independent of the level of climate change that we encounter. So for me, where that leaves us is that the focus on action on climate shouldn't really be on a decision about whether we should make crushing investments in unknown technologies. What I take away from this material is that we have a lot of options that are very attractive. They're either no regrets options where they're going to pay for themselves independent of how much climate changes, or they're low risk options where we're likely to build a better world in any context, and a much better world in the context of climate change. And I see these no regrets, low risk options really playing out in several areas. I already talked about adaptation, increasing preparedness for current variability. Disasters currently account for about 0.2% of global GDP loss. If we could cut that in half, that'd be billions of dollars a year. If we can slow rates of removal of rainforests, we can decrease carbon emissions, improve both ecosystem values and carbon accounting at the same time. Lots of studies indicate that around the world we're very inefficient in the use of energy, and that we could increase the efficiency of our buildings and transportation by typically about 30% in a way that wouldn't cost anything, would actually make money for society. So energy efficiency represents a huge tree with low-hanging fruit for progress on climate. There's lots of discussion about energy independence and strategies for moving us away from dependence on getting all of our energy from countries with unstable or hostile governments, and being able to produce energy at home from solar panels or windmills or nuclear power plants or biofuels are all attractive. The President in the State of the Union address a couple of days ago talked about the opportunities for increasing employment in clean technology. It's clear that a lot of the new technologies for energy independence can result in decreased air pollution. The air pollution issue is probably the dominant one in many of the world's rapidly developing countries, especially China and India. And then, you know, one of the things we would like to do with a portfolio of no regrets or low risk options is make livelihoods more attractive. And things like biofuels or rural wind farms are ways to kind of spread the wealth. And I know that the idea of spreading the wealth is not a popular one, but I use it in the context of making more wealth for everybody. So, you know, I think this is a pretty compelling case, but I started out by telling you that I wasn't as good a communicator as a political cartoonist, and so I'm going to end with another political cartoon. And, and the challenge that we face in climate communication is that, you know, there's a lot of people out there who think that it's all a big hoax. What I hope I've shown you tonight is two things. It's not a big hoax, that the scientific community has a huge mass of information that really characterizes not only what we know, but the important things we don't know and how those introduce risk into the system, but also that there are lots of options we can take that are smart regardless of the amount of climate that occurs. And you know, my answer to the what if it's a big hoax question is that even if it were a big hoax, it'd be worth making these investments. And since we know it's not a big hoax, it's even worth it more. I want to just spend 1 minute thanking the people whose data I drew on shamelessly in presenting this material. So Carolyn Snyder is a wonderful PhD student who just finished last year. She worked with Steve Schneider and me. Bill Anderegg's another PhD student who worked with Steve Schneider and me and has done a beautiful study on the sudden aspen decline. A postdoc, Scott Laurie, worked on the velocity of climate change and pulled together a mountain of interesting information for that. And my colleague, Ken Caldera, was the lead investigator on the studies on the permanence of climate change and the emissions commitment from existing infrastructure. And finally, I'd like to thank a dear colleague, Steve Schneider, who we lost tragically last year, who was the inspiration for much of the work that I talked about tonight. So thanks very, very much. I'd be happy to take questions, and I know there's some kind of technology to facilitate that. I don't know what it is.
Yeah, the technology should be pretty good in here. If we can get the lights up, maybe that'd help a little bit to see hands. But if you'll raise your hand, stand where you are, and state your question, I think we'll be able to hear it, or so everyone can hear, and Dr. Fields can respond.
I don't know, do we need microphone runners?
Using your nails analogy, I mean, in terms of removing carbon dioxide, is there any place for that in this scenario?
Yeah. So the question was, what do we know about technologies for removing CO2 from the atmosphere? And in the set of technologies that are called geoengineering, there are a number that are CO2 removal. Some of these involve increasing natural sinks, either by fertilizing the oceans so that more CO2 goes into the oceans, or fertilizing terrestrial ecosystems so that trees grow bigger and take CO2 from the atmosphere. The capacity of those sinks to take up extra CO2 is probably quite limited. It's not going to be a big player in this overall equation. But there are options for CO2 removal that could be facilitated by humans in a more labor-intensive way. And I'll mention a couple of examples. There's a brilliant geophysicist at Columbia named Klaus Lochner that's developed these sort of artificial trees that have a CO2 scrubbing material on them that would allow you to basically have like a CO2 catcher up in the atmosphere and move the CO2 out and either convert it into a mineral form or compress it and inject it into the ground. My favorite technology for CO2 removal is that we already know how to burn biomass in regular combustion-based power plants. We're getting to be better and better at using biomass in integrated gasification combined cycle power plants. And if we took, let photosynthesis occur, back to Steve's introduction about how plants grow, and harvested plants, combusted them for energy, and then took the CO2 that resulted, compressed that, and pump it into geological formations. In Southern California, that would mean mainly into depleted oil and gas fields. We would result in production of energy with a net removal of CO2 from the atmosphere. In the new set of scenarios, these sort of pictures of the way the world works, the lowest one that the IPCC is using has negative emissions, CO2 removal after 2050. Nobody knows how that would work or how much it would cost, but it is something that's getting more and more conversation. Just let me give you a number for framing. The current carbon emissions from the energy system are about between 8 and 9 billion tons of carbon per year, resulting in about 35 billion tons of carbon dioxide release. If we were to take 1 billion tons of that and sequester it underground, that would require a technology infrastructure about the same size as today's complete global oil and gas technology infrastructure. So it's a big, big problem. But it's not a problem that is totally outside the range of possibility. One of the reasons I think it's an interesting one is that I would much rather have the oil companies be on my side than against me in this, and presenting a series of compelling opportunities for them to be a part of the solution rather than the problem seems like it might be a good starting point. Which I guess I could take a follow-up. I don't know if can I take follow-ups? Sure. Okay, well, go ahead, follow up.
What about bacteria? Airborne photosynthetic bacteria. It would actually think green clouds that would filter, the feasibility of having a filter in the atmosphere that would be able to reach that low concentration.
So the big problem with rapidly growing photosynthetic organisms is that they don't live very long, and so you got to do something with all those bacteria. That's the big problem with producing biomass energy from algae, is that, or fertilizing the oceans. If the algae die and decompose in an hour, the CO2 is back in the ocean. And so the thing you need to think about in coming up with a solution to the problem is what you're going to do with the stuff. Let's just say we found an organism that we could float in the atmosphere, and that floating, just for the sake of argument, 1 billion tons of bacteria in the atmosphere wouldn't have any negative impacts on how much sunlight reached the surface. I would still have billions of tons of dead bacteria I had to figure out something to do with, essentially bury, if that kind of strategy was going to be useful. So it's, there are lots of possibilities, but somehow you got to permanently put away the carbon that's fixed, whether it's fixed in photosynthesis or chemically.
Bacteria would continue.
Well, then you're going to have the whole atmosphere be solid bacteria after a while. I mean, somehow you got to do something with the stuff, but then not taking up any more CO2. The way organisms sustain themselves is by releasing CO2. We should probably go on. I'd be happy to talk more with you about this, but it's an equation that doesn't help you unless you can lock this stuff away permanently.
It looks like the IPCC was projecting up to a 5.5% investment in GDP to try and avoid the potential consequences of climate change. And then the cost of not dealing with climate change would be about 5%. So how do you convince politicians to invest maybe 0.5% more in GDP than would actually be the cost of not dealing with it whatsoever?
So that's a really good question. And as you noticed on the impacts, the costs of unabated climate change were anywhere from 5 to 20% per year. The cumulative cost of mitigation was -1 to 5.5%. And so part of the question is, do the ranges overlap? And the Stern Review has quite high numbers, but if you have a 5% decrease every year, that compounds, and so it results in a wealth level in 2050 that's substantially less than just the 5%. And so the thing to recognize is that the nature of the impacts is occurring every year, starting when the climate change starts and continuing forever, really leads to a much bigger overall impact than the cumulative impact. And if I had been able to think of an efficient way to show those things in comparable terms, that would have been obvious. In the back there.
Hi, you talked about this at the very end. I'd like you to just elaborate it on just a little bit. There are many in the mainstream media who are quick to discredit a lot of your own research and a lot of the research that you did cite today during the summer. Some even suggest that climate change doesn't even exist. What do you have to say to those people, and what is your opinion on why this idea is so pervasive in light of all of the scientific data?
Yeah, so the question is, why is there so much skepticism? And I think that there are a bunch of reasons. One of the reasons that there's lots of skepticism is that it's to the benefit of certain stakeholders to cause that skepticism. It's a wonderful new book by Naomi Oreskes called Merchants of Doubt, and it characterizes the organized efforts to create skepticism about the science of health consequences of tobacco, acid rain, secondhand smoke, nuclear winter, and climate change. And it basically shows how in each of those examples there were stakeholders who were interested in the maintenance of the status quo, who very purposefully and strategically made investments in identifying, recruiting, and training scientists to inject doubt with the idea that by being a merchant of doubt, they might delay or prevent action on the issue. One of the amazing thing about that book is it's the same exact people in all of those issues. And if you look back at the history of health consequences of smoking and climate change, the same exact experts were the skeptics. I won't comment further on that. But so there are other reasons. There are some people who, from religious grounds, feel that humans just couldn't possibly impact the whole world. If people approach this as an issue of sort of foundational faith, I don't think that the science-based arguments are going to be compelling. And then, this is really messy stuff, and I think that I showed you guys how much uncertainty there is in the data. One could present exactly this information and say, wow, there's so much uncertainty, that can't possibly be enough basis for making smart decisions. I would argue the opposite, but this question of how much certainty you need is, I think, probably the most important one, and if you guys carry away any message from my comments tonight, I hope it's the idea that we don't need to know everything to make a good decision. We need to know enough. And I feel that we do know enough to make smart decisions about investments that are very likely to pay off.
So if most of the problem is due to, power plants, and especially old technology, so how much do you think it really matters on individual action scaling up? Like if you were to tell people to just fly less, are you advising people on that, or?
Well, I could go on for hours about the consequences of different kinds of mitigation options, and the question is, which are the really high leverage ones? And if you look at the overall picture is that, roughly speaking, it's about a third of the emissions come from transportation, about a third of the emissions come from buildings, and about a third of the emissions come from making stuff. And all of those represent real opportunities for improvement. And the way I think about it is that this problem has some components that need to be addressed at the international level, has some components that need to be addressed at the national level, many components that can be addressed at the level of individual households. I think that California's leadership on fuel-efficient vehicles and electric vehicles has been a really impressive demonstration of how consumer demand can really push solution set. But the fact of the matter is that, currently it's cheaper to make electricity from coal than it is to make it from photovoltaics, and unless consumers either demand that their electricity come from photovoltaics, or there's some kind of incentive in the system that levels the prices, it's going to take a long time for the photovoltaics to come in. At least the current evidence isn't that they're going to come in based on having the price drop so low by scaling. But I think that individual action can be effective in the case of the power plants. I don't know if in Southern California you have the option of buying 100% renewable energy. A lot of consumers do make that choice, but consumers can also express their preferences through the ballot box. And I think that if the part of the problem that's going to get solved by incentives is going to get solved, it's got to get solved by by having political leaders who can work at the international scale make this a priority.
That another could present the facts that you've presented and reach different conclusions, or say that we don't have the necessary information to make a decision. Is there some dissent in the scientific community regarding the conclusion that you've reached, or is it fairly unanimous?
Well, most of the material about the range of uncertainty that I presented comes from the Intergovernmental Panel on Climate Change. Really unique organization. It represents a partnership between the scientific community and the world's governments. And the IPCC essentially engages and assesses the scientific opinions of all the world's experts who contribute to this topic, and kind of assembles them into a picture of what we know and what we don't know. And I would say that the information that I presented captures sort of the 99% of what people think, and the other 1% is typically from sources that aren't in the regular scientific literature, and it's really not possible to assess them. So the IPCC statements are very, very conservative. Let me just say one thing about the way the IPCC process works. The summary for policymakers, that probably what you would have seen from the IPCC, is approved word by word, by consensus, by every one of the countries of the world. So if I was asking for IPCC approval on, for example, the statement that warming in the climate system is unequivocal, I would put that up on the whiteboard. I'd be standing in front of a group of about this many people. The typical IPCC plenary has about 150 countries represented. And I'd say, does anybody have a problem with the idea that this statement is consistent with what the underlying science says? And I wouldn't move off of that statement until everybody agreed. It's an incredibly high standard of not only scientific agreement, but buy-in by the world's countries. Back there? Yeah, you.
Considering that over the history of the globe, there's been like a cyclic warming and cooling period, do you think that this trend is part of that period?
Yeah, so the question is, given that we've seen cycles of warming and cooling in the past, is it possible that this is part of that? And the best understood cycles of warming and cooling over the past million years or so are the ice ages. And we have a good understanding of what causes the ice ages. In fact, the way that the ice ages work is a critical component of our understanding of the role of greenhouse gases in climate change. The ice ages are caused by the fact that the Earth's orbit has these little wobbles in it. And sometimes the Earth is tilted a little bit more toward the sun, sometimes a little less. The orbit, is not exactly circular, and sometimes a little more oval, and sometimes it's a little less oval. And these wobbles in the orbit result in slight changes in the relative amount of sunshine that hits the northern hemisphere and the southern hemisphere over periods of tens of thousands of years. And we've seen in the last 800,000 years, 6 periods when the world was dramatically cooler than now, about 6 C cooler than now, and there were a couple of kilometers of ice over much of the northern hemisphere. We've seen other periods when it was about the same temperature as now. During the ice ages, the CO2 concentration was about 180 parts per million. During the interglacials, it was around 280 parts per million. Today, it's around 390 parts per million. So we don't have any experience in the last million years with CO2 concentrations that are even close to as high as we have now. But what we know is that the physics of the wobbles in the Earth's orbit are all highly predictable. Newton actually knew how to calculate that. And as a consequence, we know that we're not in a period where the recent warming is caused by ice age type mechanisms. So it must be caused by something else. The very interesting feature of what we've gotten from the information about the ice ages is that we can calculate with a lot of precision how much the changes in the solar radiation due to the wobbles in the orbit should have changed the climate, how much extra energy we got in the climate system. And we also know how much the CO2 changed, and we know how much the extra CO2 should have absorbed energy. And so we can partition the influence on climate between the orbital part and the CO2 part. And when you do that, you get a number for the CO2 sensitivity of the climate system. And those numbers are one of the lines of evidence that feeds into the CO2 climate sensitivity that I showed you, is this 2 to 4.5 C that the IPCC talks about. So the answer to your question is that there's essentially zero possibility that the warming we've seen in the last century is related to an ice age type mechanism.
Why don't we take one more question?
Okay.
We were given some figures on the economic sacrifice that would be required, but given different countries, different voters, forms of government, and where they're at in their industrialization, is it realistic that Western countries could see -1 to 5.5%?
So the question is, what are the likely distributional consequences of dealing with climate change? And, you know, the main reason that the world hasn't come up with a comprehensive international strategy for dealing with climate change is exactly this. Whose responsibility is it to make the investments that are going to solve the problem? And the U.S. says, gee, look at how fast emissions are increasing in China and India. Don't they need to take the lead? China and India say, we're responsible for a historically negligible part of the emissions, and our per capita emissions are still only a fourth of what yours are. Obviously, you need to take the lead. And, you know, somebody smarter than me needs to figure out what the way forward is. I mean, personally, if I start from a consideration of the fairness issues, it seems to me that the approach that was taken in the Kyoto Protocol, which says that the industrialized, high-emitting countries need to take the lead in developing the solutions, makes sense. If I step back and say, well, where are the economic opportunities from leadership with the industries of the future, it also seems to me that it would make sense for countries like the U.S. to try and position itself as a leader in the energy technologies that are going to power the 21st century. So I think the answer to the question is that I don't really know whether or not the cost could be constrained to that limit if the investments were focused in a subset of the world's countries. But I can think of a lot of reasons that it makes sense for leadership on this issue to come from the countries that have the most capacity to make the changes, from the countries that have the best technology to push the solution set, and that have the historical responsibility for solving the problem. And I want to say that in the framing of not blaming the United States or any other industrialized countries. And we and the rest of the industrialized world developed a magnificent energy infrastructure that supported a vast amount of global economic growth. But I think we've reached the end of the sort of arc where that's the best thing to do. And the real question for the future is whether the leadership emerges to act on the new opportunities in the shorter term, where we can still reach the CO2 levels where we can have a high confidence that climate change isn't going to be at the damaging extremes, or whether we don't wait. Thanks so much.